Welcome to The Explainer. Today, we're taking a look at an invisible enemy that is constantly trying to bring down modern aircraft. It doesn't use missiles, and it doesn't use bad weather. Nope, it uses rogue waves of energy. We're talking about electromagnetic interference, or EMI. If you've ever wondered how a massive metal tube packed with millions of wires and highly sensitive computers manages to fly right through thunderstorms and intense radar fields without just completely short-circuiting, well, you're in the right place. Here's our flight plan for this explainer. We'll define the invisible threat of EMI, dissect the anatomy of how it attacks, and uncover the 3 factors that cause it. Then, we're gonna look at the solutions, designing the armor, wiring rules, and finally, heavy-duty grounding and bonding. Let's get into it. Section 1, the invisible threat of EMI. What exactly is it? So what is electromagnetic interference? Simply put, it's the presence of unwanted voltages or currents, which can adversely affect the performance of an avionics system. Think of it as rogue electrical noise. You know, in a modern aircraft, you've got navigation systems, engine controllers, communications, all of them relying on extremely precise electrical signals. EMI is the static, it's the disruption, it's the unwanted party crasher that threatens to totally scramble those critical signals. And the stakes here, they're incredibly high. This isn't just a minor annoyance on your radio, this is about absolute flight safety. The effects of EMI can be downright terrifying if left unchecked. We're talking about actual errors in instrument indications. That means a pilot's gauges could read both above and below the true values. Plus, it causes these high-pitched heterodyne whistles on audio comms, making it basically impossible to hear air traffic control. It creates weird herringbone patterns on video displays, and honestly, worst of all, it can trigger unwarranted alarms. Just imagine a cockpit suddenly filling with false fire warnings while a pilot is trying to land. That level of distraction is exactly what engineers have to eliminate. Which brings us to Section 2, the anatomy of the interference. Let's look at how the stuff actually attacks. The sheer scale of this battlefield is massive. The threat spectrum starts all the way down at 300 Hz, what we call extremely low frequency, or ELF, and spans all the way up to 30 GHz, or super high frequency. Aircraft are just constantly bombarded by different frequencies. I'm talking power lines, radar transmitters, fluorescent lights, and even the microprocessors humming away within the plane itself. And this energy basically has 2 primary ways of sneaking into our sensitive systems: conduction and radiation. Conduction is when the interference travels through physical, electrically conductive paths. Think circuit wiring or the actual metallic structure of the aircraft itself. Radiation, on the flip side, is when that electromagnetic energy broadcasts invisibly through non-conductive paths. Stuff like the air, plastic materials, or the fiberglass nose cone of the plane. So it's either sneaking directly through the wires or it's beaming invisibly right through the air. Okay, let's pause for a quick pop quiz pulled straight from an aviation maintenance manual. Let's see how well you're tracking the nature of this noise. What exactly is aperiodic noise? Take a second. Think about what that word means in the context of electrical signals. Got it? The answer is predictable but not continuous. If you nailed that, awesome job. For a little context here, engineers categorize EMI in 3 main ways. You've got periodic noise, which is continuously repetitive, like a steady, annoying hum. Then there's random noise, which is totally unpredictable, like environmental static. And finally, aperiodic, which is predictable, but it only happens every so often, not continuously. Knowing your enemy's rhythm, that's the very first step to blocking it. Moving right along to Section 3, the 3 factors of EMI. This is a fundamental engineering concept, what I like to call the rule of 3. For an EMI problem to actually exist, you absolutely must have 3 things present at the exact same time. First, you need a noise source, something actively generating that rogue energy, like a switched mode power supply. Second, you need a means of coupling, basically a pathway for that energy to travel, either through conduction or radiation like we just talked about. And third, you need a susceptible receiver. That's a sensitive piece of equipment, like a radar receiver or a microprocessor, that just can't handle the noise. Think of this as the EMI triangle. Now, here is the absolutely crucial point, brilliantly summarized right in the source material. To reduce the effects of EMI, at least one of these factors must be addressed. That is literally the golden rule of electromagnetic compatibility. You don't have to fix all 3. If you can trap the source, block the path, or toughen up the receiver, you break the triangle. And boom, you defeat the threat entirely. So, with that golden rule in mind, let's move to Section 4. How do we actually design the armor to break that triangle? The very first line of defense attacks factor number 1, suppressing the interference right at its source. Before the noise can even escape, engineers trap it. They enclose noisy equipment in grounded, screened metal boxes. They use transient suppression to kill those sudden and nasty voltage spikes. They twist and shield bus wires to basically cancel out magnetic fields. And they intentionally keep pulse rise times slow. Why? Because a sudden sharp change in a signal releases way more electromagnetic energy. By smoothing out those changes, the noise stays trapped. But what if you can't trap the noise? Well, then you move to strategy 2, cutting off the pathway. We reduce the noise coupling. Engineers will physically separate power leads from sensitive signal wires to prevent crosstalk. They'll swap out standard wires for screened coaxial cables, or even better, optical fiber data buses. And since fiber optics use light instead of electricity, they are literally immune to EMI. Total game changer. They also throw in isolation transformers just to break up any interference ground loops. And the final strategy? If the noise still somehow gets through, you increase the susceptibility thresholds of the target. Basically, you toughen up the receiver so it just completely ignores the noise. This involves limiting the bandwidth and sensitivity of the receiver to only what is strictly necessary. If a radio doesn't need to listen to a super wide frequency band, you just narrow its focus so it doesn't even hear the surrounding static. You also make sure all internal screens are tightly fitted, and you select components that are just inherently less susceptible to stray fields right from the get-go. Let's move to Section 5 and talk about the aircraft's physical nervous system, its wiring and cabling. In a confined space like an airplane fuselage, you've got thousands of potential EMI sources crammed right next to really sensitive receivers. So maintaining electromagnetic compatibility here requires unbelievably strict wiring rules. First, adequate wire separation must be strategically routed and totally maintained. Second, wire lengths have to be kept as absolutely short as possible to minimize coupling. And check out this fascinating detail from the manuals. When wire shielding is used for lightning protection, the shield grounds, which are called pigtails, cannot be altered. Literally adding just an extra inch or two to the length of a ground wire will seriously degrade the lightning protection. Precision is absolutely everything here. You simply cannot lengthen equipment grounds beyond their exact design specification, or the impedance changes and it's suddenly no longer a true ground.
Finally, we arrive at Section 6, the heavy armor. Grounding, bonding, and protecting the aircraft against HIRF, or high-intensity radio frequency fields.
So, let's talk about bonding. You see these heavy braided metal cables? Those are bonding straps, physically connecting different structural parts of the aircraft together. And this isn't just about structural integrity, guys. It's a massive electrical imperative. By bonding everything together, engineers ensure that no single part of the aircraft builds up an isolated static charge. They're effectively turning the entire outer skin of the plane into one continuous unified shield. And this goes hand in hand with grounding. Grounding is the process of electrically connecting conductive objects to either a conductive structure or some other return path. But why? Well, to safely complete a circuit, to provide a safe return path for stray current, and honestly, most importantly, to protect the aircraft, the crew, and the passengers from the absolutely devastating effects of a lightning discharge. Effective grounding ensures the electrical integrity of the whole aircraft structure. But to do this effectively, the tolerance they work with is unbelievably strict. When maintenance crews perform bonding and grounding checks, the resistance required is usually less than 0.001 to 0.003 ohms. Just think about that for a second. That is essentially zero resistance. It has to be a flawless electrical connection. If the resistance is even slightly higher than that, the energy from a lightning strike or a super high-power radar transmitter won't flow harmlessly away. It's going to find a way right into the sensitive avionics. Okay, let's wrap this up with one last interactive challenge regarding HIRF, high-intensity radio frequency. We know manufacturers design specific avionics areas to be heavily shielded against it, but, things break down over time. According to the maintenance manuals, what do you think is the primary cause of HIRF protection failure in an aircraft? The primary cause, unserviceable radio filters. If those built-in filters fail, all of that heavy armor we just talked about is totally compromised. So the next time you step onto a commercial flight, just remember, you are trusting a meticulously maintained, entirely invisible shield. It's a silent, constant war fought by engineers every single day. Balancing ohms, twisting wires, checking braided straps. just to ensure the invisible noise of our modern world doesn't pull us right out of the sky. So next time you look up and see a commercial jet, ask yourself, are you looking at a flying machine or a perfectly tuned flying Faraday cage? Thanks for joining me on this explainer, and keep questioning how the incredible world around you actually works.